Hey students, got another great question. Let me give this one a shot here. This is again more on magnetism. It's from the chapter 22 on magnetism, although it's from the harder book, the University Physics chapter 12, and it's number 27 here. And it says here, looking at this figure, it shows two long, straight, horizontal wires. Now let me pause right there because kind of the first thing popping into my mind is that in this chapter, we learned that there is a magnetic field from a wire. It makes loops around the wire. We use right-hand rule number 2, and let's talk about that. But it looks like we've got two of those wires. Okay, let's see what I say. Oh, horizontal wires that are parallel and that are a distance of 2a apart. If both wires carry a current of I in the same direction, A, what is the magnetic field at point 1? And then B, what is the magnetic field at point 2? So we're going to look at this one first and then this one here. And of course, we can't actually do any numbers. And so I think that kind of makes it harder for people because there's no numbers. So this is going to be all symbols here at the end. But as I put here A, I'm going to realize then that looking at point 1, there would be a magnetic field created from each of these. And so maybe the first thing to begin with is to say the total magnetic field needs to be from number 1. And so let me call this upper wire number 1. And then also wire number 2. And so I need to add these two fields together. Okay. Now, as I do that, you can see that they said these were the same current, right? If both of them carry current I, yeah. This distance is the same A. And so what is possibly going to happen, let's talk about it, is that these two are the same magnitude. And if they're the same magnitude in the same direction, then it's just double it. If they're opposite direction, it's a 0. Now, if they're at 90 degrees, then we got to do Pythagorean theorem. And so we got to look at the direction as well as its magnitude. So from wire number 1, let me put in the number, mu naught I and 2 pi. And let me call this A. And so the distance away would be A. And so this would be the magnitude of it. Now, to do its direction, this is where that right-hand rule number 2 is going to come into play. And so I'm going to imagine taking my right hand and grabbing this upper wire. And you can see then if my thumb is the current, the field, as it kind of circles around, would be going in. And so the traditional symbol for inward is a circle with an X. So from your vantage point, it's going into the screen. In my case, it's into the piece of paper. Okay. And maybe I'll just down here in my equation say into screen. Okay. And then I'm going to add to that the magnetic field from number 2. So this will be mu naught I over 2 pi A. So again, we're the same distance away. So that's why I was saying that with the same current, the same distance away, both of these wires are going to make the same strength of the magnetic field. But again, using that right-hand rule, and so imagine grabbing with my right hand again, and so I'm grabbing this wire, but now I'm grabbing wire number 2, okay, so thumb's pointing, and this point then is above the wire, so the field is coming out, and so you can see how my fingers curl around. They're saying, come out, and then go around. So that's why number 1, as it comes out and goes around, was going in to the screen, because it was below this wire. But for number 2 here, my fingers curl around and come out. So the traditional symbol for coming out is a circle with a dot. And so maybe I'll put here out of the screen. And mathematically, we could call, coming out like the z direction positive and going in the negative z direction. And so one's positive, one's negative. I don't even think we have to do really that much work. I'm just going to say they're equal in magnitude, they're opposite in direction. The answer is then 0. And so at point number 1, the fields end up canceling off. Okay. Part B is going to be that same argument. The total field is going to be the field from number 1 and then the field from number 2. Now, right away, we could see that we are not the same distance away from the wire. In fact, wire 1 is twice as far as wire 2. See, wire 2 is a distance of 2a, but wire 1 is now a distance of 4a. And so because of that, when we apply this equation, we're going to be saying 1 is stronger. The field coming from number 2 is actually stronger. And since it's in the denominator and inversely proportional, we're going to end up saying it's twice as strong as the field from number 1. So if they're in the same direction, we wouldn't be quite doubling it. If they're opposite directions, it wouldn't cancel off. If they're at 90 degrees, we'd have to do a Pythagorean theorem here. But I think you can begin to see that point number 2 is below each wire. And so if I apply a right-hand rule to either wire 1 or wire 2, and as my fingers curl around, they're going to be going in for both cases. And so if I call this number 1 and this number 2, they're going to be in the same direction, and so I'm going to be adding their field strength together. Or if you want to call inward a negative number, I'm going to have two negative numbers that I'm going to be combining together to make a larger negative number going into the screen. And it's that, I think, part of this problem was to get you to realize that in between the wires here, they're going to be opposite in direction, and down here, they're going to both be in. And it's not part of the problem, but if they asked us to do the magnetic field above the two wires, they both would be coming out. And so we would, above the wires, we would, add them together coming out. Below the wires, we would add them together going in. But between the wires, they'd be competing with each other, one in and one out. Okay, so coming back to the mathematics, if I say, what is the strength of the magnetic field from number 1, I would say it's mu naught times I over 2 pi. And now my distance away from number 1 is 4a. And so that would be its magnitude. And again, let me just write into, implying into the screen. And the other one would be mu naught I over 2 pi, and the distance is then 2a. See, because we're a distance of 2a from wire number 2. And that 2 would be into the screen. And so when you take into and you add it to into, you get into. And so we're going to combine them together here. Okay. Maybe the way to look at this is a common denominator here of 8 pi a, because this is a 4 pi. So if I put a 2 up there and put 2 down there, now I have a common denominator of 8 pi a, because 2 times 2 times 2 times pi times a is 8 pi a, just like 2 times 4 times pi times a is 8 pi a. And of course, then now the numerator you can see is twice as big as that one, and that's what we were saying. This from number 2 is twice as big as number 1. And so when we take a 2 and add it to a 1, we get a 3. And that's, I guess, all we can do. We can't actually put in any numbers because this is a unknown, and this is unknown. Although we could put in this, which is 4 pi times 10 to the minus 7, and then we could do some canceling. Well, maybe I will, but I don't think that's necessary. Because if we put 4 pi times 10 to the negative 7 for the permeability of free space, together with an 8 pi a down here into, we could then cancel and leave a 2. And so in the numerator, we would have 3 times 10 to the minus 7 times I. And in the bottom, we would have a 2 over a and into. And I suppose we could even then put it as a 1.5 times 10 to the minus 7 I over a into. But I have a feeling that your solution guide will probably just have that. All right, well, hopefully that was helpful for someone. Take care.